started optoelectronics yesterday. That's the study of the nature of electromagnetic radiation. So everything within the electromagnetic spectrum, from gamma rays straight through to radio waves with visible light in between. If we're using those and manipulating those in some kind of way, that's what optoelectronics is. We've got increasing wavelength as we go further up here. So radio waves are the longest waves that we have in the electromagnetic spectrum. Gamma rays are the shortest that we have. We've also got our wavelengths of violet light here and straight through to red light on the other side. That's the range of visible light. Put them all together, you get white light, and that's what we see. Everything outside of that we don't see, but we can use and we can manipulate for various purposes. Frequency increases as we're going this way. So gamma rays have the highest frequency energy. You notice that X-rays are quite high frequency, as are ultraviolet. Those are the kind of dangerous ones, because those are the ones that have a lot of energy. All of these waves travel at 3 × 10⁸ meters per second. They all travel at the speed of light, but they have different frequencies and wavelengths, but the kind of ratio of those to each other, the product of frequency times wavelength, is always constant. It's always going to come out at 3 × 10⁸ meters per second. So all the stuff we're going to look at to do with optoelectronics, we're all looking at the manipulation of the parts of the electromagnetic spectrum. So what we started out with was irradiance of radiation. And now irradiance is the power of the radiation per unit area. So the amount of radiation that's fallen on a given surface. We set up an experiment to figure out what the relationship between irradiance and distance was, and moved a light detector backwards and forwards to see how it affects the irradiance of light that is at the detector. Compiled those results into a short table and graphed 2 graphs. First graph was irradiance against distance, and we noticed that as we increase the distance, the irradiance decreases. So the amount of radiation falling per unit area decreases. That's what we would expect, because as you get further away from a light source, just like as you get further away from the sun, you get less heat and you get less light. You basically get less radiation falling on that particular area. So the irradiance decreases. We then plotted irradiance against 1 over the distance squared and found that that was in direct proportion. So irradiance is in direct proportion to 1 over the distance squared. If we rearrange that, we get that irradiance times distance squared is a constant, and that extends us to this equation here, I1d1 squared equals I2d2 squared. That's really an inverse square law, which basically means that as you double the distance, you will quarter the irradiance. Or if the distance becomes twice as close, the irradiance will get 4 times bigger. So inverse square laws are quite common in physics, and this is really the first one that you've encountered. But because we know that I times d is constant, we can figure out missing irradiances or missing distances for a variety of quantities.